Hi, PreCalculus kids. This is section 6.3 on graphing rational functions. And I'm going to do this video just slightly different than I normally do because it took us an hour in class yesterday to just do 2 pages. So if I actually start from scratch with this one, it's going to be a 2-hour long video and ain't nobody want to hear me babble about math for 2 hours. So I'm going to take what we did in class yesterday and talk about it. You can pause the video if you did not get a chance to copy these things down. But here's what my graphic organizer looks like. We're going to come back and use these things from this graphic organizer throughout this whole section. So the deal is, one of the first things I talked about was that you've got to factor first. What is a rational function? Well, a rational function, they call it r of x, is some polynomial in the numerator and some polynomial in the denominator. But remember, denominators can't equal 0 because that would be an undefined fraction. So you're going to take whatever's in the numerator, you're going to factor it. You're going to take whatever's in the denominator and factor it. And what you're looking for are wholes. If they have a common grouping in the top, you'll see this in an example in a few minutes. If they have the common grouping in the top and the bottom, you can cancel it. And if they cancel, then that creates a hole. You know there's a hole. It's actually a removable discontinuity. Remember those from way back when? A removable discontinuity, that's a hole. You can remove it. You can cancel it out. And so you're looking for holes, and that happen when the factors cancel. Because what you're going to do is use then, if they do have that situation where factors cancel, you're going to use the more simplified version of the function to answer all the rest of your questions to be able to graph it. Now, some things that come into play with rational functions are horizontal and vertical asymptotes. Sometimes there's a slant asymptote. They happen every once in a while. You're going to be looking for x and y intercepts, and you're going to be talking about domain and range as we go to graph these things. So job number 1 is, for your rational function, is to factor first. And really you're looking for holes. They happen when the factors cancel. Probably the most popular of our rational functions is this guy, the 1 over x function. Looks like this. We've seen this before as a parent function. Remember, we talked parent functions a while ago. This guy's a parent function. It is the 1 over x graph. It's painted actually on my classroom wall with the can't touch this next to it, because you can't touch the y-axis and you can't touch the x-axis. They are vertical and horizontal asymptotes for this particular graph. All right, so that's probably one of the most popular ones. So first things first. Again, pause the video if you need to copy these things down if you didn't get a chance to do that yet. Vertical asymptote, what is it? It's a vertical line that the graph approaches and never touches. You can never, ever, 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 ever cross a vertical asymptote. It's like you come up to a dead-end street and you either have to turn left or right. You can't go over it, right? That's kind of what these vertical asymptotes are like. You come up to this asymptote, my dead-end street, and you either have to go right or left. It's got to go one way or the other. It's not going to cross over. So here's a picture, what it looks like. Usually we use dotted lines because it's not actually part of the graph, but it's important to the graph. So you put a dotted line there. And then they always have to be, because it's a vertical line, x equals some number wherever it is. So we call them VAs, vertical asymptotes, and they always have to be x equals some number. By the way, that x equals is important because you're actually talking about the equation of a line. You can't just say 2, because 2 is just a number. 2 is just a point. This one is x equals 2 because it's actually the equation of a vertical line. So make sure you have the x equals with it. It's very significant. So how do you find it? This is the most important column that you're going to be using as you go to graph it. Set the denominator equal to 0 and solve for x. That's how you find it. All right, horizontal asymptotes are similar. Horizontal line the graph approaches. But guess what? There are times when graphs cross horizontal asymptotes. I would say like 80% of the time they don't. But there are times, the other 20% or so, where it can actually cross it. You could even have 2 different horizontal asymptotes within the same graph. So they're a little funky, these guys. They're a little special, these horizontal asymptotes. So we're going to say rarely instead of never. Now my picture, I'm going to put one that doesn't cross. This one, I made mine at y equals 3. See how it's now a horizontal line? Horizontal lines have to be y equals a number. And so in this case, it's y equals 3 for my picture. So every horizontal asymptote, is going to be y equals a number. How do you find them? Well, the deal is you compare the powers. Now, if you have 3 situations that could happen when you compare the powers. You have the bigger power on top and the smaller power on the bottom. I'm talking about the highest power, the degree of the numerator versus the degree of the denominator. So if you have the bigger power on top and the littler power on the bottom, there are none. There's no horizontal asymptote. I mean, think about it. If you had x cubed over x squared, you get an x, and he's just an x. Like, there's no issue with that. However, if you flip it around, if the littler power is on the top and the bigger power is on the bottom, x squared over x cubed, now I have 1 over x. And you can see that that's a whole different story. You've got a variable in the denominator. So anytime that happens, the littler power is on top and the bigger power is on the bottom, it's automatically the x-axis, which we call y equals 0. They're one and the same. Y equals 0, x-axis, they're the same thing. Now, if they're the same powers, if you've got the same power on the top and the same power on the bottom, then it's going to be made up by whatever their coefficients are. Now, that gets a little bit dicey, but I kind of gave you an example when we flipped over our note packet when we talked yesterday doing these. Let me show you. I want this part of it. So I just made this up. If I have 3x squared plus 6x plus 1 over 2x squared minus 7, see how the powers are the same? I have an x squared up top and an x squared on the bottom. I have to take the numbers in front. They're coefficients. And they make up what my horizontal asymptote would be. And again, remember, it has to be y equals, you need that there. Don't just put 3 halves. So the horizontal asymptote is y equals 3 halves, the coefficients on those variables that have the same powers. Okay, so we kind of talked about, so I could give you an example. This box just wasn't big enough to say all that. Okay, now we're on to slant asymptotes. Slant asymptotes, they're slanted lines that the graph approaches and never touches. So again, I've got an asymptote. Here's my picture. And this is actually the equation of a line, right? This is a y equals mx plus b thing. You're going to have some kind of form of a y equals mx plus b because it's a straight line. And again, we do it as a dotted line. These don't come up that often, but here's when they do come up. When the power on top is 1 more than the power on the bottom. So say you have an x cubed over an x squared. The power on top is 1 more than the power on the bottom. And in order to find it, you're going to use long division or synthetic division, which is why we talked about that back in the last unit. So long division or synthetic division for that guy to figure out those slant asymptotes. All right, x-intercepts is where the graph crosses the x-axis. Here's a picture. Again, you have 2 choices of how to write it. You can write it as x equals -1 or write it as a coordinate, -1, 0. Either way is fine, your choice. And how do you find it? You let y equals 0 and solve for x. Now that's for any x-intercept for any function at all. But there's a special case because of these rational functions that works. And this is only for rational functions that you can take a shortcut. And if you remember, just set the numerator equal to 0 and solve for x. And I'll show you why, where the theory of that comes from. Let me pull over my paper again. The example that I used for the horizontal asymptote, I just used it again. If this is my rational function, polynomial on top, polynomial on the bottom, and I set it equal to 0, let me take this away for a second. If I set this equal to 0, and ask you to solve it. How do you solve that? Well, you're going to put the 0 over 1, and you're going to cross multiply. Remember we saw these back in section 6.1, where how do you solve rational functions? If it's a single fraction and a single fraction, you cross multiply. Well, 3x squared plus 6x plus 1 times 1 is that, and 2x squared minus 7 times 0 is 0. And you see how it just ends up to be whatever the numerator is, gets set equal to 0. Now that's the deal that we're talking about, and this is only a special case for rational functions. If this were a different type of function, that wouldn't work. But because it's a rational function, here's what happens every single time. You end up zeroing out the denominator, so it's just the numerator that equals 0. So there's a shortcut, and that's what we're saying here in our box. Set the numerator equal to 0 and solve for x. Again, just a property of rational functions. So y-intercept is next. The y-intercept is where it crosses the x or the y-axis, of course. And so in this case, here's my picture. I can write it as y equals 1 or 0, 1, the coordinate. How do you find it? You let x equal 0 and solve for y. Domain was next, all the possible x values. We've always done it this way, bracket or parenthesis, left to right. You can definitely do that. Here's my picture. I kind of chose the 1 over x graph to do this. Now if I draw this, I have two choices, and you can see I've got kind of different colors going on here. This purplish color is one way, using my brackets and parentheses. It's in two pieces. The graph's in two pieces. Therefore, the domain this way is going to be in two pieces. This piece goes from left, negative infinity, to 0. Doesn't touch either one. Well, you know you can't touch negative infinity. This piece picks up on the other side of 0 and goes to positive infinity. So that's this. So one choice I have to write the domain is writing these two things. But another choice with these guys is just to say, well, the domain is it can't be 0. It can be anything else, but it can't be 0. And so one of the shortcuts for domain for this one is that it's all real numbers, but it can't be wherever a hole is or wherever a vertical asymptote is. And you can see that that's where your vertical asymptote was at 0. So this is kind of a shorter version of writing your domain, if you like that better. But this other version in the purpley color is also valid. So two different ways you can write it, whatever makes you happiest. But we're going to probably do it more this way. Can't be the hole or the vertical asymptote. And the range, of course, is all the possible y values. Same idea. I use the can't touch this graph. And when I look at this, I can either go, I wrote these in backwards places, didn't I? This guy here, negative infinity to 0, is this guy. And this piece is 0 to infinity. So those two pieces would be my domain. Or, remember, I can take the shortcut way and say, by the way, domain's lowest to highest. Some kids, for whatever reason, want to flip that around and put the highest first and then the lowest second. That doesn't work. You got to go lowest guy on the left and the highest guy on the right. It can't be for the range. Y can't equal whatever the y value is of your hole or where your horizontal asymptote is. So in our case, our horizontal asymptote is y equals 0, the x-axis. So my range for this guy is y can't equal 0. All right, so that was our graphic organizer. That's going to be really important to us. We're going to flip back and forth to that quite a bit. So here's where the notes start. Now the notes kind of reiterate what our front page was. So we're going to kind of repeat some of this just a bit. He didn't know when he made these notes that we were going to put a graphic organizer with it. So he's thinking that you don't have that when he put these notes together. So we do. We have it. So we're going to go quick through this. What's a rational function? Polynomial on top, polynomial on the bottom. Bottom can't be 0. Okay. Sketch one of them. 1 over x. He's my most popular guy. Here he is. Can't touch this. Factor first. I put that again because we want to remember to do that. Always factor first. And so the first topic he wants to talk about are removable holes, domains, and vertical asymptotes. Well, removable holes happen when the factors cancel. Domain is all real numbers, but it can't be the hole or the vertical asymptote. And vertical asymptotes are when the denominator equals 0. And so he gives us 3 different functions, and he wants us to find those 3 things for these 3 different functions. And so that's what we were doing in class yesterday. Now, first one. Actually factors. X minus 4, 2x squared minus 8x. The bottom factors, top does not. X minus 4 stays, 2x comes out. X minus 4 on top, x minus 4 on the bottom. I'm like, woohoo, I got cancellation. And so I cancel them out, and that leaves me a more simplified version of the function, which is 1 over 2x. This is what we're going to use to answer all the rest of the questions about this function because we've taken this hole away. Where's the hole? Where x minus 4 equals 0. Solve it out, x equals 4. So you've got a hole at 4 when x equals 4. The next thing he wants me to find, it's easier to find the domain if we talk about the vertical asymptote first, right? Because your domain is going to be everything but that vertical asymptote. So might as well go to the vertical asymptote first. That's when the denominator equals 0. So when x equals 0 in this case. Well, what is the domain? The domain is everything but the whole or the vertical asymptote. So domain is everything but 0 and 4. So domain is x can equal 0 and 4. I wrote it here, but I thought it was too small, so I wrote it out in the margin. It just means the same thing. I just wrote it bigger so you could see it better. There you go, first one. Second one, this one, nothing factors. All right, factor first doesn't work. Don't got anything going on with that. So the next thing I want to go for, so there's no holes, in other words. I can't factor it. There's no factor cancellations, no holes. Vertical asymptote, when I set the denominator equal to 0. Well, check that out. I end up into imaginary territory. Well, we're trying to graph this thing on a real coordinate plane. That's not going to work. So there are no vertical asymptotes for this guy. If you get anything that's imaginary anywhere along the line, it's not part of your graph. Well, if it doesn't have a vertical asymptote and it doesn't have a hole, his domain's all real numbers. Third one doesn't factor either, but I can go for the vertical asymptote, take the denominator, set it equal to 0, get -1. My domain's going to be everything but that. Can't be my vertical asymptote. There you go. There's the first three. All right, then he takes and adds on, all right, let's talk x and y intercepts. So to find a y-intercept, you let x equal 0 and solve for y. To find an x-intercept, you set the numerator equal to 0 and solve for x. Again, that's a special case for rational functions. Normally, for any other function, you would let y equal 0 and solve for x. But for our case, this is going to work. All right, I'm taking the simplified version, the 1 over 2x. I want to find the y-intercept. I let x equal 0. Put a 0 in. 1 over 0 is undefined, which means there's none. If I take the x-intercept, I take the numerator and set it equal to 0. Well, can 1 ever be 0? Nope, can't be, so there's none. Second function, to find the y-intercept. Now, I did this one the long way, plugging in a 0 for each of the x's to show you how this thing goes. But really, it comes down to, if my x is all 0 out, I'm left with just what these constants are at the end. So I've got -3 over 4. There you go. You're done. So you can kind of do that in your head is what I'm saying. You don't necessarily have to write this whole thing out with the zeros in there. But this is the theory behind it. X-intercept, I take the numerator and set it equal to 0. Now this one, I had to go and do an AC method. I think I did it on another piece of paper when I did it. But -18, find the factors of -18 that add up to be a +7, divide by the leading coefficient, and you end up with this. X equals -3/2 and x equals 1/3. So this was factoring. We've done that before, AC method, solving it out. So there's my x-intercepts and my y-intercept. This guy here, y-intercept, let my x's be 0. I end up with 5 over 1, which is 5. X-intercept, take the numerator, set it equal to 0. What happens? Oh my goodness, I end up back in imaginary territory, so that means there are none. And then the last thing we talked about in class was the degree for finding horizontal asymptotes. So I'm comparing the powers. When the degree in the numerator is bigger, big over little, there's none. When the degree in the denominator is bigger, little over big, it's y equals 0, which is the x-axis. And when the degrees are the same, I take the coefficients, whatever the coefficients are. So here's some examples of that. Where is the bigger power? Well, you can either go back to the original one and look, or you can look at our simplified version. Where's more x's? Well, there's only one x that's on the bottom, so it's a little over big. Little over big is y equals 0. If I take the second one, these guys have the same powers. Square and square. Take the numbers in front. 6 over 1. That gives you 6. So I've got y equals 6 is my horizontal asymptote for the middle guy. And then the last one, I've got x squared over x, big over little. That gives me none. Okay? And that's where we left off on Friday in class. So we're going to pick up from there with the rest of this stuff. So the next guy we've got is this slant, or they sometimes call them oblique asymptotes. And they happen, we kind of said this on our graphic organizer, when the degree on top is 1, exactly 1, more than the degree on the bottom. I guess I could get more mathematical. I think I can fit the word bottom in here. I could get more mathematical and say the degree in the numerator is 1 more than the degree in the denominator, but you get it. Same idea. And then what do? How do you find it? And we said on our graphic organizer that you use long or synthetic division. And what you're looking for is a y equals mx plus b type of thing. You're looking for some kind of straight line equation. So they show you that, guess what, that third equation we've been looking at, x squared over x, he actually has a slant asymptote. And I know that because a square is 1 more power than a regular x. So how do I find it? We all like synthetic division way better than long division. So here's how it goes. We're going to set it up for synthetic division. Well, x plus 1, it's kind of like you're taking, I guess back in the day we would have seen it this way, x squared plus 5 divided by x plus 1, right? That's the same thing. So the divisor is x plus 1. Take x plus 1, set it equal to 0. I get a negative 1. That's what goes out in front of my synthetic division doohickey. And inside, right, we're going to take the divisor and we're going to put the coefficients from that. But remember, you need a missing term. There's a square. It goes from a square to a number. I'm missing an x. So in my divisor part, I'm going to have a 1, a 0, and a 5. So don't forget the missing parts. They're still there. The missing powers, you've got to put them in. So drop the 1, multiply, negative 1, add, negative 1. Negative 1 times negative 1 is 1, gives me a 6. I'm done. So what does this equate to? I have x squared, so that means that this would be an x minus 1 with a remainder of 6. Well, guess what? I don't care about remainders in this case. This is my slant asymptote equation. You ignore that remainder. So let me write myself a note. I'm going to even put it in a different color. I ignore the remainder. I'm just using the y equals mx plus b part. So my slant asymptote would be this right here. So here's the last piece they want me to do. They want me to now graph these things. And you say, oh my goodness. All right, so let's go back to the very first things that we talked about with these functions, right? Back to here. Let's do one at a time. So the first one, the whole is the last thing you're going to put on there. The whole is the last part of this. Your vertical asymptote is at x equals 0. So let's put that on first. Vertical asymptote at x equals 0. Vertical, here it is, along the y-axis. Now while I'm on asymptotes, let's go down here. Here's my horizontal asymptote at the bottom here. Where's that guy? He's at y equals 0. That's the x-axis. Let me put that on my graph. So here I am, putting horizontal asymptote. And you notice I'm just kind of a little bit above it because I want to be able to see that it's actually there. So I got my vertical asymptote, I've got my horizontal asymptote. The next piece I want are my intercepts. So let's go to where we found the x and y intercepts for this guy, and there are none. Okay, which kind of makes sense, kids, because think about my graph. I have an asymptote here, and I have an asymptote here. It's not going to touch those places, right? So it's not going to cross the x-axis, and it's not going to cross the y-axis. Kind of makes a little bit of sense. All right, so how am I going to figure out where the rest of this graph goes? I have, I'm looking to see if they gave me anything else that I can say for this guy, and there really isn't anything else to say. So there's a couple different things I can do. Thing number one that I can do is I can go to my calculator or Desmos and put my function in. Now remember this simplified to 1 over 2x? Or I can kind of make a quick table of values. Like say for example, I'm going to put it down the bottom here. Say for example that x is 1. Oh, you can't see me. Now you can see me. If x is 1, put a 1 into here. I get a 1 over 2. I get a 1/2. How about if I put a -1 in there? I'll get a -1/2. Well, let's plot those 2 points. If I'm 1/1/2, I'm in this neighborhood. And if I'm -1, -1/2, I'm in this neighborhood. Do you remember how these rational functions tend to look? And hopefully you're saying, yeah, they're supposed to be like kind of like that can't touch this graph. And this one's extremely similar because the can't touch this is 1 over x. This is 1 over 2x. So you can see they're extremely similar functions. So I'm going to graph this thing, and it goes like this. It kind of curves. It's not quite so boxy, but so that's what the graph looks like. Now you can go to Desmos, like I said, or graph it on your calculator if you have a graphing calculator, and it's going to show you that picture to verify that you're correct. But there's one last piece that we put on hold, and that's the hole. The hole is at 4, so I have to put an open circle. I'm going to make it bigger than it should be, so I can be pretty clear that I've got a blank spot right there because there's a hole that came out of that thing. If you graph this on your calculator or you graph it on Desmos, you're not going to see the hole. The pixels in the program that graph these functions, they go right on over that. However, if you put it in the table, if you put 4 into the table and check out the table values, you'll see that it's undefined. So it's there, it's just you can't visually see it most times on a graphing calculator or on a Desmos type application. All right, here comes the next guy. Let's see. We have, I'm going back to our vertical asymptotes first. We have nova. I'm looking at the middle guy. We have nova, but I do have a horizontal asymptote at 6. So I'm going to put my asymptote at 6. Horizontal at 6. Ooh, way up here. I do have an x-intercept at x equals 1/3. That's where it crosses the x-axis. And I do have a y-intercept at -3/4. They're kind of close together, aren't they? Now this one I do have to go to Desmos and put in because this one's really goofy. This one doesn't fit the scenario of anything. See how it doesn't have the vertical asymptote like the other guys did? Let me show you. For the sake of time again, I'm going to just show you what the graph looks like. You can plug this into Desmos. Oh, by the way, when you do, make sure that you put the numerator in parentheses divided by the denominator in parentheses. When you enter that into Desmos, you need those parentheses in there for you to get the right picture for this. All right, so here's what it looks like. It comes down. Hold on one second. It comes down. It looks like this, and then it goes over and back under. And you're like, what on earth is that? That's a crazy picture. That one there's a bit nutsy. But that's your story. All right, then we're on the last guy. Last one, if I'm looking, he has a vertical asymptote at -1, so that's the first thing I'm going to put on there. He has no horizontal asymptote. So at -1, I'm putting on a vertical asymptote. But he does have a slant asymptote. He's the guy with the slant asymptote up here at x-1. Now think about this, how you graph a line. Y equals mx plus b. We graph the y-intercept first. That would be down here at -1. And then I use the slope to get the next point. So I'm up 1, right 1. Up 1, right 1. And you can see just by putting my dots for these lines how this slant asymptote is going to work. Does it have any intercepts? Go back over here. Let's see. I do have a y-intercept of 5, but I do not have any x-intercepts. So I'm going to put my y-intercept at 5. There's my dot. And then I'm going to go to Desmos and I'm going to graph this thing. So when I go to Desmos and graph it, here it goes. Hugs the asymptote, does a little UB, comes up and hugs the slant asymptote. It kind of like the slant asymptotes seem to create like an X. See, they kind of look like an X. And you're either going to have your graph be inside the X, like this guy goes, or outside the X. So it's kind of like you're either inside or outside the X when you have slant asymptotes. All right, so let's try one from scratch. We kind of did all the stuff for those 3 functions there. We're going to look at this guy. And again, I'm going to do this relatively quickly. We'll explain more deeply in class if you need it, but I'm factoring first. That's always your first deal. The top, everybody's got an x. That leaves me with 2x squared minus x minus 1 on the top. And everybody on the bottom, he can be factored. So can this 2x squared minus x minus 1. But this factors into x plus 1 and x plus 1. The top, let me go a little taller here. I have the x I factored out. 2 times negative 1 is negative 2. I need the factors that multiply to negative 2 but add to negative 1. Divide by the negative 2 to give me my new groupings. AC method is what I'm talking about. Here's what I got. And you say, well, that's cool, but nothing cancels. And you're right. So you have no holes. We can, I guess, write ourselves a little note over here. There are no holes. Nothing cancels. And don't think that you just wasted your time by factoring all that stuff, because when you go to find your vertical asymptotes and setting your numerator equal to 0 to find your intercept, all that stuff is this is going to make your life easier. So you didn't waste your time on that. There are no holes. Let's go for the vertical asymptote. My vertical asymptote is going to be set the denominator equal to 0. Well, I have x plus 1 equals 0. And I have it again, x plus 1 equals 0. Do I need to write it twice? No. You just need to know where that's going to happen, and that's going to be at x equals negative 1. So let's put that on our graph. At negative 1, I have a vertical asymptote. Okay. My y-intercept. Well, my y-intercept is when I let the x's be 0. 0, 0, 0. So I have, this is looking for the y-intercept, I have 0 on top. 0, 0, 1, I have a 1 on the bottom. 0 over 1 is good. You can have that. That's it's just you can't have a 0 in the denominator. So this is 0. So y equals 0, I have an intercept right there. Put him on your graph. The x-intercept comes from setting your numerator equal to 0, and lucky for us, we have that all factored right here. That's going to make our world really easy. We know that x has to equal 0, this guy that I factored out. We know that 2x plus 1 has to equal 0, and we know that x minus 1 has to equal 0. This guy has 3 x-intercepts. X equals 0 is fine. This one, swing the 1 to the other side, it becomes negative. Divide by 2, you get x equals negative 1/2. This guy, swing the 1 over, he's going to give you x equals 1. So let's put them on there. Well, the 0 is already there from the y equals 0. Negative 1/2 is, oh gosh, can I even fit that in there? I'll try to, there you go. And positive 1 is over here. Well, that's really funky. That's got some weird looking stuff going on. So we'll have to see what happens with this guy. Horizontal asymptotes, let's compare the powers. The power on top is a cube. It's probably easier to go back to the original. The power on the bottom is a 2. So in this case, if I'm thinking about the horizontal asymptote, I have a big over a little. Therefore, there's none. But then I need to go for the slant asymptote. check it out. Does it have a slant asymptote? And we say, yeah, I got a cube over a square. The power on top is one more than the power on the bottom. So this one has a slant asymptote that I need to find. That's going to take me some doing. Now, by the way, if you have a slant asymptote, you're never going to have a horizontal asymptote, because think about it. The power on top is one more than the power on the bottom. You'll always have a big over little situation. So if it has a slant asymptote, you won't have a horizontal asymptote. They don't work together. Now I'm looking at this thing. If I go back here, I've got to divide this to be able to come up with where the slant asymptote is, where my y equals mx plus b equation would be. And so if I look at this guy, I have to use long division because I don't have a single value to put out in front of that synthetic division sign. So anytime you have a polynomial with a square in it, you've got to use the long division. So I'm going to come down here to the bottom, and I'm going to give myself some room to find this. So set up the divisor, x squared plus 2x plus 1. Set up your dividend, 2x cubed minus x squared minus x, and then I guess a plus 0 as a placeholder there. So you're going to go and do your firsts. I don't know if you remember this from a few weeks ago when we did long division, but 2x cubed divided by x squared is a 2x, goes up top. Multiply it through. 2x times x squared is 2x cubed. 2x times 2x is 4x. 2x times 1 is 2x. And then we color penciled this, if you remember. Change the signs. Two x cubes cancel. I have a negative 5x squared, and I have a minus 3x, and then a plus 0. Well, here's the nice thing about this. When I take the next round and do negative 5x squared divided by x squared and get a negative 5 and put it up here, I'm done. I don't need anything more, because remember, this is your y equals mx plus b equation. You don't have to complete that long division. You just need what the x piece is and what the number is. You can stop at that point. The rest of it is meaningless. Okay, so it's not too bad. So let's graph this thing. Negative 5 is down here, my intercept. And then I have a slope of 2. Now this is going for my my slant asymptote, slope of 2, so I go up 2, right 1, up 2, right 1. And I'm going to connect these in a dotted line and create my x, right? Now this one does some strange stuff. You're going to go to Desmos and you're going to put this in your Desmos, and you're going to see that it skates along the vertical asymptote, comes up to this leftmost intercept, goes up and down, and then goes along this slant asymptote. How about that guy? He is a wacky looking guy. He's got all your pieces though. This is probably one of the more difficult ones that we'll look at. All right, flipping the page, let's see what we got next. We're getting close to being done. Here we go. Here's a U-try. Well, you can take a pause to the video and see if you can try it, but let me work my way through it with you. This one's really not so bad. Not like the last one. The last one was really ugly. All right, so what's the first thing you're supposed to do? First thing you're supposed to do is factor. This guy factors. He is two numbers that multiply to negative 12, add to negative 4. You have 6 and 2, x minus 6, x plus 2. Now at this point you should be able to factor. That's why I'm kind of going pretty fast through that. You should be able to do that factoring pretty easily. I need two numbers that multiply to 6, add to 5. I get x plus 2, I get x plus 3. Whoa, check it out, I got a whole. Right? I got an x plus 2 here. I've got an x plus 2 there. I'm going to cancel those puppies, and I'm going to talk about a hole. My hole is at x equals -2. Because it's when x plus 2 equals 0. Take the group you got, set it equal to 0, hole at x equals -2. Now, I don't graph that until the very, very end, because that's where it's going to come. I've got to put that big red circle on my graph to say, don't have a point here. Now, what I'm going to use then for the rest of this problem is the simplified version of my fraction. I don't have any room on the right to put it, so I'm going left. I'm using x minus 6 over x plus 3. That's what I'm using to answer all the rest of my questions. So vertical asymptote, my va, is when the denominator equals 0. My denominator is x plus 3. That equals 0 when I get x equals -3. That I can put on my graph. Vertical asymptote at 1, 2, 3. Y-intercept, when my x's are 0, what do you get? 0 minus 6 gives me a -6 up top. 0 plus 3 gives me a 3 on the bottom. -2. That's going to be where my x-intercept is. Toss a circle on there. Oh, y-intercept, my bad, 2. Y-intercept at 2. Put it on the right axis, winner. X-intercept, when you take the numerator, set it equal to 0. X minus 6 equals 0, x equals 6. Cool. X equals 6 is over here. Toss a dot. Horizontal asymptote, slant asymptote. Check out your powers. They're the same power. X on top, x on the bottom. I can even go back to the original. X squared on top, x squared on the bottom. They're the same. If they're the same, you take their coefficients. And so your horizontal asymptote is a y equals, and the number is 1 divided by 1, or 1 divided by 1, depending on which fraction you look at. Still 1. So horizontal asymptote at 1, toss that on your picture. You can go to Desmos and graph this thing. Why do I feel like I put this in the wrong spot? Oh, I did. Did you catch it? I'm catching it now that I'm looking at the picture. This isn't going to make sense for how my values need to go. I graphed this guy wrong. Y equals -2. I'm having trouble with that guy today. Oh, wait, no. That wasn't what I want. Yeah, my y-intercept should be at -2. Here it is. That makes more sense to me. Things should line up, by the way. You'll see it. And if I had not caught that before I graphed it on Desmos, I'd have caught it when I graphed it on Desmos. Because here's where it goes. This function goes this way. It's over here and over here. Your points have to line up or else it just won't make sense. But I'm forgetting one thing, or I'm not really forgetting one thing. I've got a hole, and my hole is at -2 when x equals -2. X equals -2, go to -2, follow it down. Now these are approximate graphs. You're sketching the graph. These are not like, you're not rocket science specific. But if I'm at -2, then I'm over in this neighborhood and I've got a hole on my graph. My red pen's running out of ink. There's a hole there. This guy's a holy graph. And I got to make sure I say so. Okay, so you want to make sure that you put that on your graph. Well, there's all the examples and such. Remember that you are not doing the skills review, so I'm going to put a big old X through that. We don't do that. But you are doing the practice problems, and I'm going to do one more problem with you that's going to incorporate all this stuff. Find the holes in the vertical asymptotes. I think you know how to do that. Find the x and y intercepts. That's the next set. You can do that. Find the horizontal asymptotes. I know you know how to do that. Find the slant asymptotes. You know how to do that. That's synthetic or long division, depending, if it even has one. So let's go to the actual graphs. That's numbers 13 through 16. And I'm going to see if I can pick one that I think is the meanest. And that would be 14. I think number 14 is the meanest of them all. So that's the one I'm going to pick to do as my last example with you. It's again pulling everything together, putting all the pieces together from our graphic organizer. The only thing that they don't do on this that I really do want to talk about are domains and ranges. So we will look at that maybe at a point in time. But for now, to keep it consistent with where the notes are, here's what we've got. We can go back and look at domains and ranges maybe at the very end. So I have to factor first. Factoring first makes me take out an x on the top, leaves me with x squared minus x minus 20. On the bottom, nothing factors out, but I do have an x, two numbers that multiply to -3, add to -2. I can factor that bottom. I can actually factor what's in the parentheses up top. Let's see what that does for me. That's going to be an x minus 5 and an x plus 4. Numbers that multiply to -20 add to -1. Okay, so there I am. Nothing cancels, no holes. No holes. But I do have a vertical asymptote. Actually, interestingly enough, guess how many I have? I have 2. Because I have one where x minus 3 equals 0, and I have one where x plus 1 equals 0. I can have multiple vertical asymptotes. So this one, when I swing the 3 over, is at x equals 3, and this one is at x equals -1. Oh, I'm checking out a picture here, and I'm thinking we might need to go back and change a definition that we had going on, but we'll do that when we get there. Okay, so vertical asymptotes. One's at 3. Whoop. Over here. And one's at -1. Y-intercepts. Probably easiest to go back to this guy. I'd have a y equals 0, 0, 0 on top. Everybody's got an x, so all that, remember, all the x's become 0. And on the bottom I have a 0, 0, -3. Well, 0 over -3 is 0. And so I have a coordinate right there, a y-intercept at 0. X-intercept is when the numerator equals 0. So I have an x that I factored out that's going to equal 0. I have an x minus 5 that has to equal 0. And an x plus 4 that equals 0. So I solve them. Swing the 5 over, x equals 5. Swing the 4 over, it's x equals -4. Here is a 5. And here's a -4. The 0 was already there. Let's talk asymptotes. If I talk aha, let's see my situation, big over little. So there are none. If I think about powers, does it have a slant asymptote? Cube over square. Oh man, the power on top is one more than the power on the bottom. I gotta do this whole thing. And on top of that, it has to be long division because I've got a squared divisor. And I'm like, ugh, right? Let's start it. Remember, you don't have to do the entire problem. You're stopping after you get the mx plus b part. This guy is an x cubed minus an x squared minus a 20x, and then I guess a plus 0 up there. So x cubed divided by x squared is an x. X times x squared is x cubed. X times -2x is -2x squared. X times -3, -3x. Change the signs. Negative, positive, positive. Combine like terms. Cubes cancel. I have a -1 plus 2 is a plus 1, so I have an x squared. I have -20 plus 3, I get -17x's plus 0. And then I just have to get what this next value is. If I take x squared divided by x squared, I get 1. So my slant asymptote, I'm going to go into this next box because I just don't have room. My slant asymptote is x plus 1. You don't have to complete that division. Remember, you just need to get to the y equals mx plus b part. So if I graph this, this guy is a positive 1 with a slope of 1. The b is 1, so I put a little dot there, slope of 1. And I just keep a few points so I can draw that slant asymptote, which is this guy. All right, so then I'm going to go to my friend, Mr. Desmos, and I'm going to graph this thing. And so when you do that, here's what you come up with. You come up with it's skating along this slant asymptote and then going up and hugging that vertical asymptote. And then the next thing you come to is this middle guy, and you'll see the middle guy actually kind of does a little cubic shuffle like this. And the last guy skates along the vertical asymptote, goes through your intercept, and goes off towards the slant asymptote. So there are two things that, well, there's one thing that comes up for sure that we need to go back and fix. Do you know what it is? Do you know? Do you know? Graphic organizer, here it is. My slant asymptote, the slanted line the graph approaches and never touches. Guess what happened? That guy just crossed through it, didn't it? So we need to fix this. We were wrong with the word never. We're going to fix that and call that rarely. Okay, so fix that on your graphic organizer. Rarely crosses it. This one happened to do that. Check him out in the middle. He crossed right on over that darn slant asymptote, didn't he? All right, since I have you and your captive audience, let's go back and look at, I want to look at domains for this guy. We'll just take this guy for example, domain and range, because we haven't talked domain and range. So since I'm into this box, I'm going to keep it in this box, domain. You have choices. You can either do it as the parenthesis bracket method. That would put you at negative infinity to negative 1 with parentheses, negative 1 with parentheses to 3 with parentheses, and then 3 to infinity with parentheses on both ends. So if you did it that method, that's what you would say. In our method, we know that domain x can't be wherever I have a vertical asymptote, which is at negative 1, and at positive 3. And there are no holes. So this is a way easier way of saying my domain. It just can't be the vertical asymptotes. And remember, I'm getting that from right here on my graphic organizer. X can't equal the whole or the vertical asymptote. Do I really need the all real numbers with it? Not really. It's just being redundant. This is saying the same thing. It can be anything, but it can't be those. Okay? So there's my domain. My range is the lowest to the highest. Well, this one actually hits everything, doesn't it? It goes low forever and goes high forever. Each piece of this does the same. There are no gaps. There's no problems with any horizontal issues. So this one's going to be all real numbers for my range. The other way to look at it, if I go back again to my graphic organizer and look at what my range would be, it's everything but it can't be a hole. We didn't have a hole. And it can't be a horizontal asymptote. I didn't have a horizontal asymptote, so I didn't need to worry about that. So that would be my domain and my range for that last one. Let me go back to, let's try domain and range for, let's try domain and range for this first one. This is back with these examples that we did with those first graphs. And I promise this is where I'm going to stop. Okay. So my domain for this one is, it can be everything, but it can't be where there's a hole or where there's a vertical asymptote. So x can't be, where was my hole? Do you remember? It was at 4, right? X can't be 4 where I have a hole, and it can't be where I have a vertical asymptote, and that would be at 0. The range can't be where I have a horizontal asymptote. Y can't equal, my horizontal asymptote is at 0. But here's what I wanted to bring up. This is kind of interesting. And it can't be where there's a hole. Well, that means I need to figure out what the actual coordinate is for that hole. I know that the x value is 4, but I don't know what the corresponding y value would be, right? It's a coordinate, a hole, it's a coordinate on your graph. You have an x value, you have a y value. So what you need to do is take that 4 and plug it back into your original equation to figure out what the corresponding y value would be, to figure out where this coordinate really is. So if I do that, I'll just do it up here in green, it's going to be 1 over 2 times 4, or 1 over 8. Well, that's what my y value is in my coordinate for my hole, which is also going to affect my range, because my range can be anything except the horizontal asymptote or the y coordinate from the hole. Yikes. So some domain and range issues in there. All right, so that takes care of section 6.3. You can shoot me an email if you've got questions, or we're going to finish this up actually in class when I see you again on Tuesday. So have a great weekend. It is the weekend. And I will talk to you soon.